Okay. So it's already 11. I think we should get started. So this class, we're going to continue our introduction on the wastewater treatment. So if we do a recap of our last class again, so last class, we mainly introduced the properties of the wastewater. So the properties includes physical properties, for example, the color. The wastewater is normally black or grayish color, right? And then the odor is unpleasant, right? And there are solids, suspended solids, and generally the wastewater has a very high concentration of the suspended solids. So it's around, if it's for medium streams, right, the medium level of pollution, it's around 200 milligram per liter, right? And then in terms of the chemical process, the chemical properties, there are a lot of organics, right? So that we have to measure the BOD5 or put regulations on what should be the BOD5 after we treat the wastewater. So there are also nitrogen species, for example, ammonia or nitrate, which is a major nutrient for the algae bloom. So there are also phosphorus in the wastewater. So we have to deal with these nutrients before we discharge it back into the nature. So that's why there are regulations. So basically the EPA has regulations on what should be the concentration or the standards for wastewater before we discharge it, right? And then I think a quite easy number is this 4530 number. So it's 45 milligram per liter. So both for the BOD5 and for the suspended solids. Okay, so the 45 is the weekly average. The 30 is the monthly average. So we also introduced why these two averages, average values are different. This is mainly because there are fluctuations in terms of these contaminants, right? So for example, the BOD, there can be high values, there can be low values. So if it's doing weekly average, and if it happen to be in this high concentration range, then we should use a higher standard. And if it's for weekly average, then we can use a lower standard as a regulation, right? And then we watched a video about how does the wastewater treatment system work, right? Wastewater treatment plant work. So for this process, we mainly divide the wastewater treatment into several treatment processes. So we have the primary treatment and the secondary treatment. And for some wastewater treatment plants, we can have the tertiary treatment. Okay, so it's basically stage 1, 2, and 3 for the wastewater treatment. So for the stage 1, what happens is it's going to directly deal with the raw sewage, right? So basically the dirty water, dirty wastewater, and then we can pass it through the bar screens to first remove the larger particles, and then we can pass it through the comminutor to cut it into different pieces or to smaller pieces of solids. And then we can pass it through the grit chamber to remove these medium-sized particles. And then for this very small particles, we're going to pass it through the primary clarifier. So the primary clarifier mainly remove particles based on gravity. So basically, the particles are large, right? And because of gravity, they can settle down onto the bottom and then get collected. And then the relatively clean water coming out of the primary clarifier, then let's say for the federal requirement, we have to do the secondary treatment process, which means that we have to pass these relatively clean water into a secondary treatment process. And for the secondary treatment, it's mainly the aeration tank. Okay, so the aeration tank, what that does is basically we introduce bacteria into these treated water. So if you imagine what's happening in the nature, right? So we introduce the DO sag curve, right? So the oxygen is going to reduce and then come back. If you remember the dissolved oxygen, and this is time, or this is, let's say, distance. So this concentration goes down. The reason for that is there are organics in the water, and there are also bacteria in the water. So the bacteria are going to decompose these organics and cause the oxygen concentration to reduce. So basically in this secondary treatment here, the aeration tank here, we're replicating what is happening in the nature, except that we're introducing a large amount of bacteria inside. So basically this sludge or activated sludge are introduced into this pipe here. So you can think of it as we introduce a concentrated dose of the bacteria, but at the same time, we provide it with unlimited amount of oxygen. Okay, so if you have a limited amount of oxygen and you have an almost unlimited amount of bacteria, then it's going to reduce the BOD, reduce the organics concentration significantly. And this is the reason why we use this aeration tank, because if you think back on the primary clarifier, there's nothing that's dealing with the BOD, right? So the BOD is mainly the organics, right? We're just setting down based on the mass of the particles, but there's not really a process that's dealing with these organics. So that's why we have this aeration tank to deal with these organics. And basically this can significantly reduce the BOD value. And then what happens after that is, since we grow a lot of bacteria inside, so we don't want to discharge these bacteria into the nature. So we'll pass it through a secondary clarifier where these larger bacteria can settle down onto the ground or onto the bottom. So now the relatively clean water coming out is going to have a low BOD and also a low concentration of the suspended solids. So for the tertiary treatment, we can further deal with these remaining bacteria by introducing the disinfectant, let's say bacteria or virus, right, to further purify the water. But the EPA or the federal requirement says that for all the water treatment process, wastewater treatment process, it should at least have the primary treatment and the secondary treatment, right? It doesn't really care about the tertiary treatment. So one thing, another thing for this aeration tank is that in order to provide this concentrated bacteria, of course, we can just gather them from the nature and then concentrate them. But at the same time, if you imagine what is settling down onto the base here, these are basically concentrated bacteria, right? We grow them, they populate themselves in the aeration tank, they get concentrated. So basically we can split it. A part of it can go to the, actually we call it return sludge, and then mix with the treated water from the primary clarifier, right? And the remaining of them can just go to the landfill. You can just throw them away. So this is the main idea of this secondary treatment. So we're basically providing some bacteria with unlimited amount of food and unlimited amount of oxygen so that we can reduce the concentration of the organics, right? So we're going to talk a little bit more about these different steps later in this class. So before that, since we already talked about the wastewater treatment plant, which is basically a centralized method to deal with the wastewater, we also need to introduce a counterpart or a similar setup that's not used for centralized water. It's used for distributed water, okay? So those are called the on-site treatment systems. So the major difference is that wastewater treatment plant is built, let's say, nearby a city. It's dealing with the wastewater coming from all the households or some nearby industrial plants as well. But if people are living in the rural areas, then it's going to be very expensive for people to transfer their wastewater to a wastewater treatment plant nearby a city. Okay, so that's why people rely on these on-site treatment system. And actually, it serves around 25% of the population in the United States. And the other 35% is from the wastewater treatment plant. Okay, so the on-site treatment system actually serve a considerable amount of people in this country here. And among all of the on-site treatment systems, the conventional septic tank system is the most widely used system, okay? So it basically occupies around 85 to 90% of all the on-site systems. And it's also a very, I would say a very simple setup. Okay, so it has one inlet and one outlet. Okay, so you have dirty water in, which is the wastewater coming in. And then relatively clean, I would say cleaner water coming out. Okay, but of course, this water is not going to satisfy any standard, right? It's definitely not the drinking level. And also for these septic tank systems, they generally have a lifetime of around 20 to 30 years. Okay, so the way it works is for this tank here, we're separating it into two different regions. So it's called the two different compartments. Okay, you have the first compartment and you have the second compartment. So the principle is very easy. It's just using the gravitational settling of the particles. All right, so what happens is we have the wastewater being introduced into the first compartment. And then in here, since we have a lot of suspended solids, right, very large particles. So what happens is they're going to settle down onto the base. And we call these sludge here, all right? And normally these tanks have a relatively large volume compared to the flow rate. So let's imagine, basically for this septic tank, it's just serving a one household, right? So the wastewater generated from the household is not going to be very large in quantity, right? So because of this very large volume, then the residence time of the water is going to be very large, very long, right? So they can have enough time for the particles to all settle down onto, or most of them can settle down onto the base. And then in this first compartment here, they can separate into different layers, right? So you have the sludge layer, right, which is at the bottom. You have the scum layer, which are some contaminants or pollutants that has lighter density, right? So they can basically float on the top. And then you can also have the liquid level. So basically the liquid that's at the very top is going to be cleaner because the solids are too heavy and they are going to settle down, right? So for this relatively cleaner liquid, they can pass into this second compartment. So then the second compartment is using the same principle. So the larger particles can settle down, and then you can have relatively further cleaner, basically further cleaner water coming out, right? So then this is the outlet. So after the water is discharged from this septic tank, normally people would just directly drain it. So send it to a drain field. So what the drain field means is it's going to pass into a section of soil, okay? So the septic tank normally is built underground, right? And after the relatively cleaner water comes out, it's going to go into this drain field here. But as you can imagine, a lot of the water, they're going to, or some contaminants, they're going to penetrate through the soil, right? If you recall on the hydraulic conductivity, right? So these water can further penetrate through the sand layer, right? Soil layer, and further contaminate the groundwater. And this is something that we don't want to happen, because if you imagine, if there are some, let's say BOD or some heavy metals in the discharged water, and then people normally use the groundwater to serve as their drinking water, right? So if the contaminants pass around here, then we will have a problem. So that's why people also try to revise the septic tank system. So you can see that septic tank actually serve a large population, right? So 85 to 90%. But because it may cause further contamination, so people are trying to revise these systems. So one example is the septic tank system with modifications. Okay, so if you imagine in the wastewater treatment plant, one thing that we use to remove the BOD is the aeration tank, right? So this is the secondary treatment process. We introduce a lot of bubbles, right, air into the reactor and let the bacteria to grow and consume the organics. So we can use the similar principle here. We can add aeration, and then try to reduce the BOD in the tank. So we can also use the recirculating sand filter system. So this is again similar to the drinking water treatment system, right? You have the sand filter to remove the smaller particles. This is the same. We can use these sand layers to basically remove the small or medium-sized particles. Very large particles, they can just get blocked at the top, right? So in this way, we can cause a less of a pollution to the groundwater, right? So basically to reduce the environmental burden of these very easy septic tank systems. So another system that we can use is, it can be a system that doesn't have any compartments, okay? So this is generally for relatively cleaner wastewater. Because if you recall, for these wastewater, it has a lot of nutrients, right? You have the nitrogen or phosphorus. So we can actually reuse these nutrients in the plants. If we try to grow some crops, right? We can directly use them as fertilizers. But this also requires that the wastewater doesn't have a lot of organics. So the BOD generally needs to be low. So what we can use is we can use these wetland, constructed wetland. So what happens is basically the wastewater can enter from here, and then we can have the first layer, basically a first wetland to grow some plants here, okay? So the soil here is going to block a lot of the particles, and then these plants can also reuse these nitrogen and phosphorus, so they can grow upon these wastewater. And at the same time, for this first compartment or this first soil layer, we're going to use a impermeable layer. So what that means is at the bottom of this wetland, it's going to use some rock that doesn't have any porosities. So it's very difficult for the water to penetrate down. So if it's not easy to penetrate down, then we can collect all of these treated water and then send it into the second wetland. Okay, so in here we can further reuse these nutrients, right? And then here we can use the permeable layer because basically most of these solids, most of these, let's say heavy metal, they're already trapped by the soil, right? There's no way that they can further penetrate or they can further go into the second wetland here. So in this way, we're going to discharge relatively cleaner water down to the soil. So the pollution impact to the groundwater is also going to be smaller, right? So this one doesn't have any compartment here. And further, there's a modification that's called the baffled bioreactor or the BBR. So the BBR generally looks like this. It's kind of like a trailer or a shipping box. And then inside here, it has similar structure compared to the septic tank, but it's a little bit more complex in terms of how it treats the organics, how it treats the nitrogen. Okay, so what happens in this BBR here is people build different channels, let's say different baffle, to regulate the flow of the water. Okay, so for example, here the wastewater comes in, right? And you can first go over this anoxic chamber. So anoxic chamber, if you recall for the metabolism where we introduced the ecosystems, so the anoxic process is basically the process that's consumed nitrogen, right? So the first process is dealing with the nitrogen species to reduce the nitrogenous pollution from the wastewater, right? So basically we can convert either ammonium or nitrate into the nitrogen, right? And then the water will flow into this second compartment, which is the aeration zone. So this is similar to the aeration tank in the wastewater treatment process, right? We can bubble a lot of air into this aeration zone and then also introduce bacteria inside. Basically, this is going to remove the BOD in the wastewater. And then we have these channels to further regulate the flow so that the water can only go from this channel here and then down in here and then up, and then down. So basically, we're elongating the trajectory of the water. So basically, they can stay for longer, and then they can have a longer time for the particles to settle down. Let's say the suspended solids to settle down onto the bottom, right? And finally, after the water passes through all of these baffles, all of these channels, in the final channel or the final clarifier, at the top, the water quality is going to be much cleaner compared to the what's coming in here, right? So it's very similar to the septic tank, except that you have much more processes happening within this single chamber here. So here I have to mention that actually this idea of the BBR is patented by the other Dr. Wang in our department. So Dr. Jianmin Wang. So he has a company actually produce these baffle bioreactors, and it's being applied in many, many facilities. Okay, so his company is called the Frontier Environmental Technology. So if you're interested, you can feel free to hop on his website and take a look. So here, finally, what I'm showing is the treated water quality that's coming out of the baffled bioreactor, right? So basically the water quality coming out of here. So if you can see the BOD5 and the suspended solids, they're actually at very low levels. So of course there are some time, let's say January 25th, 2018, right? You have a relatively high concentration here. But if you take the average or take the full year average, these pollutants are still very low in terms of concentration. So if you recall, for the EPA standard, the weekly or monthly average, 45 and 30, right? So this is much smaller compared to the EPA standard, which means that the BBR is quite effective, right? So not only it can treat the BOD5 and the suspended solids, as we mentioned, it has the anoxic chamber, right? So we can deal with ammonia and the nitric species. And then the concentration is also relatively low compared to the EPA standard, right? So basically, these are all the on-site systems. So as you can see, the on-site system, because it's serving less of a population, and also in terms of the capacity, it's also smaller since it's normally just serving one household, right? So the process is relatively more simple, and at the same time, you can have different processes or similar process compared to the wastewater treatment plant and combine them into this compact system, right? So now let's come back to the wastewater treatment plant, and we can spend a little bit more discussion on each of these processes here. So as we mentioned, for the primary treatment, we have the bar screens, the comminutor, the grid chamber, and the primaryclarifier, right? And for the secondary treatment, we have the aeration tank and the secondary clarifier. So these are the major processes that we're going to talk about, right? So first is the bar screen or bar racks. So this is generally the first stop of the wastewater treatment plant. And also, as you can see, these bar racks, basically they work as filters, except that they have very large openings. It's 5 to 40 millimeter, which is a very large gap here, right? And this is mainly dealing with the larger species or larger contaminants. And at the same time, people need to build at least 2 channels because it's very easy to block one of the channel. You never know what people are going to dump into the wastewater stream, right? So for example, yeah, so here, as I mentioned, there needs to be at least 2 channels, mainly because if one channel is get fully blocked, the other channel can still work, right? And if you have more channels, then that will be more actually safer in terms of treating the wastewater. So here it's showing 2 bar screens or bar racks, right? So the wastewater can flow from either of them or at both at the same time, right? So you can pull them, basically, you dip them into the water, and after some time, when you feel that it's blocked, people can measure the basically the flow downstream of this bar screen. And if the flow is too little, then you're going to pull this bar screen up and then remove these larger contaminants, right? So as I said, you never know what people are going to dump into the wastewater. So actually here, I'm showing a picture that's actually making the news regarding the wastewater treatment process. So in South Carolina, there's a wastewater treatment plant called the Low Country Wastewater Treatment Plant. So I think in 2018, they made the news because the wastewater treatment plant has to shut down, mainly because people found massive collection of baby wipes, okay, or the bar screen, at the bar screen. So now you can see what kind of burden this bar screen is dealing with, right? So the baby wipes are pretty large. And then you have, if you have a large amount there, it's going to completely block these screens. And then the whole treatment plant basically have to shut down all the inflow of the wastewater and try to remove these contaminants, right? So the bar screen is dealing with these larger species. So the second step is called the great chambers, or it's either great chamber or the comminutor. So here I'm going to introduce the great chamber first. So after these larger chunks of contaminants are removed, now we're going to deal with the particles of medium size, right? So these particles are generally, let's say, above 1 inch, right? And then what happens is, while we're transferring, we're basically transporting all of these wastewater through the channel or through the pipes. What we can also do is we can create a flow that's basically let the water to spin around. So if you imagine, if there are particles in this wastewater here, and because of this spinning movement, it's going to create this centrifugal force, right? So the larger particles, they're going to spin to the outside of the channel. And then here you can have this hopper. So basically to let the particles to settle down in this collection region here. So the different designs for this great chamber has different locations of the hopper. So they can also be in here or here as well, right? So the method that we create this spinning flow is by introducing the air from the pipe in here. So if we introduce air in here, and then you're going to generate a lot of bubbles, right? So the bubble tries to float up. It's going to drag the water to go up, right? So, but the water cannot come out. So the water can only diverge in this way, and then can create this spinning movement here. So based on this mechanism, we can remove particles of larger sizes, right? And then basically can further purify the water, the wastewater. So here, this is how the channel looks like. So the influent or the inflow can go from here. And then since you have this air diffuser that's generating bubble from one side, then you're going to create this spinning movement. And the larger particles, they're just going to get spinned outside. And then you can have the hopper at the bottom to collect all of these larger particles. And you can also imagine this is actually a quite convenient way to clean the water, because we have to transport the wastewater anyways, right? Because the water has to flow in pipes, right? You cannot directly connect this primary clarifier downstream of the bar screen. You have to transport it to somewhere else. So while the water is being transported, you can introduce this spinning flow to remove these larger particles. And basically this picture is showing the great chamber, how it looks like. So the water is going to flow in this way. And then you can generate bubble from a side of it, right? So the water is going to basically, it's the other way around, right? Get spinned, and then particles can settle down, right? So this is the great chamber. And as we said, there is also a device called the comminutors. So the comminutors is just trying to cut the relatively large particles or particles of medium sizes into smaller ones. So basically, they are going to cut these particles into 1/4 inch or 3/8 inch sizes. And then to break down, so basically to crush these larger suspended solids into smaller ones, right? So the comminutor can normally be placed either after the bar screen or after the grate chamber. Okay, it really depends on how large these suspended solids are. So after they're broken down into smaller pieces, we can remove them more efficiently. Okay, so this is showing some pictures about this comminutor. Right? So there are quite compact devices, and they can crush these larger solids quite easily. So in industrial wastewater treatment process, people also design a system called the equalization tank, right? So the main idea for this equalization tank is if we try to plot what is the flow rate of the wastewater coming out of industry, okay? So normally for these industry, they work during the daytime and then they will shut down during the nighttime, right? So during the daytime, you're going to see a peak of this discharge in terms of the wastewater. But if you're talking about a wastewater treatment plant, let's draw some clarifiers here, okay? So the flow rate that's going into the wastewater treatment plant has to be a constant flow rate, right? So if the flow rate is too high, if it's not a constant, then the water might just get overwhelmed, right? It can get flow out or get flooded, right? So for this flow rate, it has to be a constant flow rate. But in terms of the industry, they can have a very strong variation based on the daily trend or based on the hourly trend here. So that's why for the wastewater treatment plant that's dealing with the industrial wastewater, we're going to build a very large basin or very large tank that's called the equalization tank. Okay, so what happens is the industry is going to directly discharge the water into the equalization tank. Okay, so and then the wastewater or the for the wastewater treatment plant, it's only going to pull the flow out of the equalization tank. So in this way, you can guarantee a relatively constant flow rate because let's say if the flow rate is very high, then it's just going to increase the liquid level in the tank here. It's not going to increase any flow rate in the treatment plant, right? So it's kind of like a buffer, right? So you don't overwhelm the water treatment plant. Okay, so basically the equalization tank is a huge tank that equalizes the flow and the quality. So not only the flow rate, but also the quality, because during the daytime, let's say in the industrial plant, they can generate wastewater with very high BOD, but at night, maybe the BOD is much lower, right? So in this equalization tank here, you can also homogenize the water quality. So it's mostly used for the industrial wastewater treatment system. So the reason why it's not being used for municipal wastewater treatment or the wastewater coming out of households is that for the households, we have the sanitary sewer. So we have these tanks or these pipes that's acting as a buffer, right, before the wastewater treatment plant. But for the industry, because the flow rate here coming out of the plant is very high, there's no way that we can use these smaller pipes or these smaller volume to act as a buffer. Okay, so this is the equalization tank. And the final stop, let's say, so here I'm also showing a schedule for the flow rate for the industrial plant, right? So you can see that based on the time of the day, right? In different hours, you see that during the daytime, let's say starting from 8 o'clock to let's say 6 p.m., right? You can see that flow rate is normally the highest during the daytime, and the flow rate becomes lower overnight, right? So that's why we need to design these equalization tanks to act as a buffer for the wastewater treatment system, right? So as I said, the final stop for the primary treatment or the first stage treatment is the primary clarifier, right? Okay, so the primary clarifier, as I said, it removes the suspended solids. Suspended. Removes the suspended solids purely based on gravity. Okay, so what happens is we're going to introduce the pre-treated water, wastewater, let's say after the bar screen, after the comminutor, after the grid chamber, and then we're going to introduce these pre-treated water into the primary clarifier. So we're going to introduce them from the center, right? The water is going to flow out, but at the same time, these suspended solids are going to drop down, right? Because of gravity. And normally for this primary clarifier, they're going to stay for a very long time, what we call the retention time. So they're going to stay in this primary clarifier for a pretty long time, several hours. Okay, so the several hours of the residence or the retention time is going to be quite sufficient to let us remove these larger suspended solids and then let them settle down onto the base, right? And further, at the edge, what people call the weir wall, right? So the relatively cleaner water can come from the outside, come from the top. And then we also call this flow as a supernatant flow. So it's basically the cleaner flow at the top, right? And we can collect them and send them into the secondary treatment. Okay, so as I said, the retention time is a quite important parameter, right? We want to basically let the water to stay for a relatively long time. So the retention time is calculated just based on the volume divided by the flow rate. Okay, so it's very similar to the water treatment system. If you imagine what is the average, what people call either called characteristic time or the residence time, or the retention time. So it's basically just the volume divided by the flow rate. So if you check the unit, the volume is going to have a unit of meter cubes, right? And then the flow rate is going to have the unit of meter cubed per second. So you're going to have a unit of second, okay? So the retention time is purely based on the volume and the flow rate of the wastewater, right? But at the same time, if you see this primary clarifier removes particles by gravity. And in the water treatment, we have a very similar device that's called the sedimentation basin, right? I think we had several homework problems or exam problems on this design here. The sedimentation basin is removing the solid particles based on gravity, right? It's after the coagulation, flocculation processes. And then at that time, we defined a parameter called the overflow rate. So basically that's the settling velocity of the particles, right? So the overflow rate is calculated by the flow rate of the water divided by the surface area of the sedimentation basin, right? So let's do another check of the unit. Okay, so the flow rate has a unit of meter cubed per second. The surface area has a unit of meter squared, right? So the overflow rate is basically meter per second. That's why we also call it as the settling velocity. Okay, so this is a definition from the sedimentation basin. So since the primary clarifier is using the same principle in terms of removing the solids, we're using the same set of parameters to design the primary clarifier, okay? So if we go back to the primary clarifier, these are generally the design parameters. And you can see that we use the same name in terms of the settling velocity. So we still call it as the overflow rate, okay? So you can have the primary clarifier that has the shape of the rectangles. It's quite similar to the sedimentation basin. And you can also have the circular ones. So the circular ones, those are just going to be a round one, right? And then basically it's the same as the schematic diagram that I draw earlier. It's this one, the circular ones, right? So here is listing some typical dimensions, and we don't need to really memorize all of these. So because you can see that they can be built in a very large range of dimensions, right? It really depends on what type of devices we're looking at. And in terms of the overflow rates or the settling velocities, so normally the average overflow rate is around 25 to 60 meters per day. And if you have a very large wastewater flow, then the peak overflow rate is around 80 to 120. So the peak, basically the flow cannot be further higher based on this condition here. So if it's above 120 meters per day, then it's not going to be efficient to remove the larger particles. And also in terms of the retention time that we talked about, it's normally 1.5 to 2.5 hours. Okay, so 1 to 2 hours. And as you can see, the primary clarifier is purely relying on the gravity, right, to remove the particles. So it's not a complete method. It's not a very efficient method to remove the suspended solids and the BOD5. So the removal efficiency is normally or below 50%, all right? So here I have an example problem. I think we can use this example to quickly know how to design these primary clarifier systems, right? So it wants us to determine what is the surface area of a primary settling tank or primary clarifier that's sized to handle a flow rate of 0.57 meter cubed per second and an overflow rate of 60 meters per day. Okay, so you can see that this value is within the range of the average overflow rate. Okay. So it's also asking what if the effective tank depth is 3 meters, what is the retention time or the detention time? Okay, so you can see that for this characteristic time, people really use a lot of names, right? So let me just write it out so that we don't mistakenly treat it as a separate parameter. So we can call it as the characteristic time, or we can call it retention time or detention time. Or the residence time. So they are all the same thing. And it is calculated by volume divided by the flow rate. Okay. So now if you look at this example problems here, so basically we have the overflow rate, which is 60 meters per day. And we have the flow rate, which is Q. And then if you recall, for the definition of the overflow rate, that's defined as the flow rate divided by area, right? So that's basically 0.57 meters cubed per second, and then divide by area. So for this problem, it's asking us what is the surface area, okay? So in this way, we can directly rearrange this equation here. So that's going to be basically the 0.57 meter cubed per second divided by 60 meters per day, right? But we should also pay attention that here the time is different. One is second, one is day, right? So we have to multiply this by 24 and then 3,600 day per second, right? And you could plug in the value and find out that this answer is 821 square meter. Okay, so this is a surface area. And then if you have the surface area, then you can calculate what is the volume. right? The volume is just the surface area multiplied by the depth, right? So we have the depth is 3 meters. So it's 820, 821 multiplied by 3. Okay. Multiplied by 3. So that's going to be this value here. And then we can further calculate what is the retention time, which is the V divided by Q, right? So 821 multiplied by 3 divided by 0.57. So you can find out that the answer is 1.2 hours. Okay, so this is a pretty simple example where we can calculate what is the retention time or what is the design for the primary clarifier. Okay, so now I think we can have a quick quiz. So if I ask you, what is the master parameter for the primary clarifier design? Let's take a choice here. So I'll give it 10 more seconds. Okay, let's stop here. So most of you are correct. So that is the surface overflow rate. Okay, so as we said, basically this is the criteria criteria settling velocity of the particles. Right, so we use that to design the surface area, and we use that to design what is the dimension of this primary clarifier. And you can see that basically this primary clarifier is very similar to the sedimentation basin in the water treatment process. Okay, so this is a primary clarifier, and we can introduce a little bit about the secondary treatment process. So as you can see from the overview of the wastewater treatment process, the secondary treatment is using a completely different principle to remove the contaminants, right? So all the processes earlier are based on the physical process. So we either filter them out or we either let them settle down based on gravity. But the secondary treatment is using the biological method. So we're introducing the microorganisms into the wastewater to remove the organics and also the nutrients from the water stream, right? So that involves the metabolism of the bacteria or of the microorganisms. So basically it's using all of the biochemical activities, right? So further, the metabolism is divided into catabolism and anabolism, right? So these are just basic definitions. We don't have to memorize them, but the major difference between these two forms of the metabolism is that the catabolism is just consuming the food, consuming the organics, while the anabolism involves the construction of the cell. Okay, so it's increasing the population. So it's like for a human being, we use catabolism to basically generate heat, right? When we try to study, when we try to exercise, but we also use anabolism to refresh our cells. We're always growing new cells, right? So these are the two forms of the metabolism. So we also use that to basically grow these bacteria and then also try to remove the BOD from the secondary treatment, right? So we're gonna stop here and we can continue on the secondary treatment in our Wednesday class, all right?